Hello, YouTube! Today we're going to start by talking about vectors. Should we have started by talking about algebra? Probably, but we're going straight into trig territory. This is the beginning of the AP Physics series, I guess. I'm going to call it a series. So welcome. I'm Latham. I do physics. Let's learn some vector math. So pretty much today we'll be talking about how to add vectors together in one dimension, which is really straightforward, hopefully, and then also add vectors together in two dimensions, which is a bit more complicated, but if you have them represented in a specific way, it's not too bad. The other thing that we'll be doing is learning about how to multiply vectors by scalars, as well as what all that vocab means. So there's going to be a lot of vocab. It's actually pretty dense, and there's kind of a lot of stuff today. Which hopefully won't be too overwhelming. Ideally, end of the day, you should be able to, if you're given a vector, find the components and the magnitude, although I think that's more so from the second half, and then add the components. So, yeah, so you should be able to do that if given it like on a grid today, and then next time we'll talk about how to do it if you just have like angles and stuff. So, first off, what's a vector? Basically, vectors are just an arrow. There are some things that are a lot more useful to represent by thinking of them as not only just saying like 5, where you've got this sort of arbitrary number meaning like this many things, right? What if instead what you want to do is represent 5 miles to the east, and that to the east is something that you want to be actually encoded in the like piece of information. So instead of having to write out the sentence 5 miles to the east, you could have some way of just having like one thing that was short that had all of that information in it. And so what a vector is instead of just a number, it's an arrow. And that arrow will have a size, but that arrow will also be pointing a certain way. So this would be 5 slightly up and to the right, and that would be your vector representation of that information. So kind of like how you can record information by like writing a word or record information with a number, vectors aren't on the way to do it. They have two big pieces to them. They have a direction and they have a size. In one dimension, for the stuff we're talking about to begin with, you can either be going forward or you can be going backwards. When you get into more dimensions, you can have more directions associated with it, and you have to be a little more careful. But for now, literally just it's either forward, in which case it's positive, or it's backwards, in which case it's negative. Sorry, forward, backwards. It's all mirrored for me, so I'm going to mess that up a lot. So, normal things that you're used to, just numbers, like again 5, or if you were to say 5 apples, numbers you use to just count a thing are called scalars. And so for vectors, just like with scalars, it's really neat because not only are you storing this information of how many apples are there are 5 apples, how long is this ruler, it's 12 inches long. Both of those would be scalars because you can't point in a direction while you're saying them. Or at least it wouldn't necessarily make sense to, or it wouldn't always be the exact same direction. So just like with scalars, you can perform operations, meaning addition, subtraction, multiplication, division, all that jazz on vectors. Although the multiplication on vectors bit, a little weirder, we won't really get to it officially in this class, although we will wind up doing it without just sort of telling you that's what you're doing. Which is kind of a running theme, because this really should be a calculus-based class, but isn't. So, when you say resultant, what that means is it's just the vector that you get after performing an operation on one or more vectors. So, if you were to be like, okay, 1 plus 2 is 3. There isn't an actual vocab word for it that I'm aware of, but the equivalent for vectors would be to say, okay, well, vector A plus vector B gives me my resultant vector, which I'm going to call C. So when I use the word resultant, it just means do the thing that I'm asking you to do and tell me about the vector that you get at the end. And it's basically just shorthand for that. So, how do we add vectors? And a lot of this will make more sense once we actually do it in context. In one dimension, really straightforward. Magnitude means size, means number. If you have a vector that is 5 miles to the west, those 5 miles to the west, the 5 miles is the magnitude, the west is the direction. So if you just take the number, you don't include plus, you don't include minus, you don't include any directional stuff, because remember, plus or minus, just directional. Minus 5, same size as plus 5. It's just that minus 5 is to the left, plus 5 is to the right, or down or up or down. You get to pick which direction is positive and which one is negative. So when you are adding the magnitudes of the vectors, just include the sign and you've done it. You've done your vector addition. So if you have a vector that is 5 to the right and 3 to the left, and you add these two things together, what you'll get is plus 5 minus 3, giving you a resultant vector of 2 to the right. Another way to do this is to do it graphically, meaning like visually, so you can actually see it. And the way you do that is you draw one of the vectors, and then, so this would be the plus 5. And then starting at the tip, meaning the arrowhead or the end of that vector, you draw the other one. So at that end, we would draw the minus 3. And when you're done drawing all of those, your last step is to draw a vector starting at where you began for the first part and ending where you ended with the last vector. And that will be your resultant. Will you have to add graphically for this class? Probably not, but it can be helpful to be able to visualize what's going on. So if this is A and this is B, then this brownish vector is the resultant of A plus B. And this works no matter how many vectors you have. If we had a third vector, vector C, that I don't want to use green, we'll use yellow. If you had a third vector, vector C, that was like, I don't know, plus 4, and you added all three of these things together, then we would start from where we ended with vector B. We would draw vector C. And that would give us a new vector, which would be the resultant of A plus B plus C, going from where we started with A to where we ended with C at the last one. And that would be plus 6. That plus means to the right. So not only are we just saying its length is 6, we're also saying that the direction it goes is to the right when we have that plus. So for me, I like explicitly writing plus signs and minus signs on vectors so that I remember that even if it's just 5, that 5 is not just 5, it's plus 5, meaning explicitly 5 to the right, which can help you keep track of the direction, which can be super useful. The other thing that I should have mentioned is that the number associated with a vector, its magnitude, is going to be proportional to how long the arrow is. So if you have two vectors, one with a size of 2, one with a size of 4, the one with the size of 4 should be twice as long as the one with the size of 2 if you're drawing it. The other operation that I want to talk about is multiplication. So specifically, if you're just multiplying by a scalar, remember a scalar is a normal number that doesn't have a direction associated with it. All you have to do is multiply the magnitude of the vector by the scalar. If the scalar is negative, negative means backwards for vector land, so negative just means make it backwards. So if this is vector A still, where we've got vector A, which is plus 5, then 2A would be plus 10, and minus 3A would be, and I'll get that in a different color, negative 15. where that plus 10 just means 10 to the right, that minus 15 means 15 to the left. Let me get my face out of the way for a sec. Ooh, did not want to move that one. Still no. And that would look like that. All right, this is going a little long because this is the first one I have done in a minute, and so I'm rambling. But let's do a couple quick examples, which are pretty similar to things we've done so far, but I do want to just quickly do this. So we'll do the first one and the last one, and you should try to do the two in the middle on your own as a double check. All right, so A and B. Vector A, if I look at it, goes 1, 2, 3 to the right. So vector A is plus 3, meaning it goes 3 to the right. Vector B is minus 2. Vector C is plus 5. 1, 2, 3, 4, 5. And vector D is plus 1. So A plus B. Couple ways we could do it. We could do it graphically, drawing vector A and then drawing vector B. And then our resultant will be from the beginning of the first one to the end of the second one. So this would be A plus B. Or we could just do plus 3 minus 2 gives us plus 1. And both of those will give the same thing. Again, vocab real quick. Vectors are just anything with an arrow, meaning a direction and a size. The size of that arrow, meaning the number, is the magnitude. So A would have a magnitude of 3, B would have a magnitude of 2, C would have a magnitude of 5, and D would have a magnitude of 1. All of these also have directions. A has a direction of plus, meaning to the right in this case. B has a direction of minus, C has a direction of plus, D has a direction of plus. B's direction would be to the left, C and D's would both be to the right. Resultant means what you get by putting them together. So the resultant of A plus B would be a vector with a magnitude of 1 and a direction of positive, meaning to the right. So 1 to the right. Magnitudes are all scalars, meaning just numbers with sizes, no direction. And that's, I think, all the vocab we've gone through. All right, real quick, just as sort of a challenge thing, I do want to do the last one. This is how you could use vectors to do some algebra. So find x if xa minus 2b equals 0. So we've got our variable of x. We've got a, which is a given. We've got minus 2 and b, also a given, and that needs to equal 0. So we can, and I'm going to try to get people used to the order on this. If you want to plug in first, you can, but typically speaking, you want to solve first, then plug in. For a few reasons that will come up again and again over the course of the year. So I want to solve for x if I'm trying to figure out what x is. So all I have to do for that is add 2b to both sides, and you can do that. That's fine. Addition and subtraction work just fine for vectors. And when we do that, what we'll wind up with is, I'm going to get this written up a little higher so that I can have more room. I'll be swapping over to paper for the more intense examples very soon. All right, so we are adding 2b to both sides. Negative 2b plus 2b is 0, so this is basically nothing on the left side. And what that leaves us with is xa is equal to 2b. I want to get x alone, and it's got this pesky multiplication next to it, so we divide each side by a. Divide each side by a. And what we're left with, because a divided by a is 1, is x, which is going to be equal to 2b over a. Now a and b are both vectors, so a little squiffy on if you can actually do this. It only works because these two things are in one dimension. You couldn't exactly do this in 2 dimensions, but for now, this will work. We'll have 2b divided by a. B is minus 2. So 2 times minus 2 divided by a, which is 3, which will give us negative 4/3 as our final answer for x. So x is negative 4/3. We take a, we multiply it by negative 4/3. Subtracting 2b from that will give us 0. I just almost asked people if there were questions, but this is YouTube, so you can't talk to me. Oops. All right, so let's try to do the same thing again with vector A and vector B. Now, if you do the Pythagorean theorem, these will have a size associated with them. Pretend I had this written on the screen already. Please. I didn't, but I should have. Sec. So these arrows have a length of 1.4 and 5 for B and A respectively. Now if I try to add those two things together, 5 plus 1.4 should be 6.4. But the problem is that if I draw, well, I guess two things. First off, is A positive or negative? Well, it's going up and it's going right. Right, we said, was positive. Up tends to be positive, so maybe we say A is positive. Is B positive or negative? B goes up and to the left. So it's kind of positive, but it's also kind of negative. Also, if we do our graphical thing, where we draw them, B looks like this. So if I draw B coming out of A and then go from the beginning of A to the end of B, it'll look like that. This arrow cannot be the same length as 6.4, because 6.4 would be how far we would go if we went in a straight line. So if we go straight from here out like this by 6.4, this will be a distance of 1.4. If we rotate that, now it's a triangle, and the triangle can't be the same length as the straight line because we had to curve, so we didn't actually wind up as far away from where we started. If you look at the blue arrow and the yellow arrow is a lot bigger than the blue arrow, although admittedly part of that is because I accidentally drew the yellow arrow a little too long. So just adding the numbers doesn't really work anymore, so we need another way to do it, and we'll come back to this picture in a couple minutes once we know how to actually do it. So I do want to talk about this other last vocab word called orthogonality. You might have heard orthonormal in a math class or orthogonal in a math class. Normally when people say that, they just mean perpendicular. It's kind of the other way around, though. Perpendicular things are orthogonal. Not all orthogonal things are perpendicular, because perpendicular doesn't necessarily make sense for all orthogonal concepts. What orthogonal actually means is that changing one of the two values will not change the other. So x and y are perpendicular to each other, but it also means in this case that they're orthogonal to each other. Because if you think about a grid, if you go up at x equals 1, you're not going to change your x value, you're just changing your y value. If you change your x value and only your x value, you're not changing your y value. So you can do that. Changing one of them isn't directly going to affect the other. Now, this primarily happens when two things are perpendicular, but there are other ways to do it. When we talk about dimensions, when we say 1 dimension, 2 dimension, 3 dimension, what that's describing, and I'll talk about this more in person, I guess, if people are curious about it, is adding a new way that you can have an orthogonal axis, meaning an axis that doesn't affect the other axes, and not break things. So in 1 dimension, you have one axis. You can go forward, you can go backwards. That's it. In 2 dimensions, we have to add another orthogonal axis. Now, if I try to add an axis at an angle, that's not really going to work. Sorry, I'm looking for like rulers or something, which I'm kind of not having. That's fine. If I have it off at a weird angle instead of 90 degrees, what'll happen is if I move along this line, it's bringing me to the right. So that doesn't work. This isn't orthogonal. But if I bend it until they're perpendicular, moving along this line up and down doesn't move me along this line left, right. And so that's a second dimension. I can add a third dimension by having forward backwards. Forward backwards is perpendicular or orthogonal to both of my previous axes. So I can go forward, which doesn't bring me left or right, or up or down. The problem gets to when you try to add a fourth dimension. Because if we try to add a fourth dimension, it's going to be at an angle so that if I'm trying to go like kind of like this, right? This is bringing me forward and back and left and right. Or sorry, this is bringing me forward and in your case left and up. That doesn't work because that's not orthogonal, because if I change one of those, it changes the other ones as well. There's an argument that the fourth dimension would be time, because if you wait, you can be in the same place at a different time without changing your place while changing your time. And so time is orthogonal to space. So there's an argument that time is the fourth dimension. It behaves pretty weirdly, though, because A, it's not a spatial dimension, and B, you can only move forward in time, and you can move multiple directions in meat space, which I'm sorry that I used that phrase. So we've already figured out that if we have one-dimensional vectors, meaning if we have vectors that are only going left or vectors that are only going right, they add up really nicely. Vectors that are not parallel don't add up nicely. So what we really want is vectors that are not parallel. The other thing that would be fine, maybe, is if we can think of things as vectors that are parallel to each other and some combination of vectors that are parallel to each other. And the orthogonality is actually the key for this. And this is something that you actually already know how to do. Because if, for the most part, I hope, because if you're looking at a grid on a, just a quadrant, if you look at this point, hopefully you can tell me that this point is 3, 4. And it's plus 3, plus 4. What this is representing is going 3 to the right and 4 up. If I draw those as vectors, beginning at where the first one is, we've gone 1, 2, 3 over to the right. If we then start there and do our second vector, 1, 2, 3, 4, that brings us to this point. If we draw our arrow going from the beginning to the end, then what we'll have is a line, or a vector, from where we started to where we ended. So if I look at the vectors, and I call this vector vector A, vector A is the same thing as 3 to the right, not going up and down, plus not going up and, or not going left, right, 4 up. And when I put those things together, I'll get vector A, which you get by going 3 to the right and 4 up. So thinking of these vectors that are at a diagonal as some combination of up and to the right, some combination of left and to the up, some combination of up, right, left, down. Left, right, up, down. Although I guess I said all 4 anyway. Some combination of those things is another way to represent them. And the real benefit of doing it this way is that any of the times that we do this, our stuff in the x direction will add together nicely, because the stuff in our x direction will be parallel to each other. Going 3 to the right and 1 to the left is not too bad to add. Any of our stuff in the vertical direction will also actually wind up adding really nicely. And when we're done with that, we can re-represent our new thing as components. So going back to our old example and actually doing it, yeah, let's just do the example. Hopefully that'll help people out, and then we'll go back and sort of dump more information. Again, today is pretty heavy, not normally this bad. The parallel components of any two vectors will add together. So what that means is, components meaning those pieces, that right, left, that up, down. What that means is we can break vector A up into its pieces. We can break vector B up into its pieces. And if we add together the pieces for A and the pieces for B, because the pieces for A are the same thing as A, or do the same thing as A, and the pieces for B do the same thing as B, taking both of those and then doing them and then adding them together will get you the same thing as the pieces for what you get by adding the final products together. It's kind of like how if for some reason you didn't really like adding two-digit numbers, you could take 12 and 14 and add them by saying 6 and 6 plus 7 and 7, and if you liked that better than saying 12 plus 14, that would work. We're doing the same thing. We're saying vector A and vector B are miserable to add. But if I think of vector A as 4 to the right and 3 up plus 3, and I think of vector B as 1 to the left and 1 up, and I write those out as a coordinate pair, plus 4, plus 3, and for B, it would be minus 1, plus 1, just like you do for grids, you do X, then Y. Then if I want to find A plus B will just be vector A plus vector B, where vector A is our plus 4 plus 3. Vector B is our minus 1 plus 1. And when I add those two things together, what I'll get is plus 3, comma, plus 4. And if I draw that out, we've got vector A, which is 4 to the right, and then vector B, which is 1 to the left. We've got vector A, which is up 3, and then vector B, which is up by 1. And so when I put those things together and draw my result, if you look on the grid, this thing is gone 3 to the right and up by 4. The components of our new vector that we get by adding the old two together are the same as adding together the components of the original vectors that we had. Couple quick reminders with that tend to throw people off. If it's just up, you don't have an x component, but the x component you could think of as being 0, so you can write it as like 0, comma, whatever. If you don't have it going up, down, if it's just going left, right, same thing, except you don't have a y component, so you don't write the y, you make that one 0. Vector multiplication still works the same way, so if you wanted to like do 2a plus b or something like that, you absolutely can. But instead of multiplying the magnitude, although you will also be able to multiply the magnitude by the number, let's say we had negative 2 times a. What that would wind up looking like is negative 2 times 4 and negative 2 times 3. So when we do that multiplication, we would get minus 8 minus 6. And our magnitude, which in this case is 5, would double as well, going to 10. Magnitude sizes can't be negative. The size of the arrow is the size of the arrow. It doesn't matter which way it's going. The direction will matter which way it's going, and the vector will be what you get by putting both of them together. All right, I probably wasted a lot of space on a bunch of stuff that I typed over here, but just in case, we're going to go through it. So there are multiple ways to represent vectors in 2 dimensions, yeah. There are 2 big ways to do it. There's more. The first one is magnitude and angle. The second one is components. For magnitude, angle, I don't have a better place to put it, so I think we're just going to do it now. You write the size of the arrow, and you write an angle away from a reference line. The angle rotation is always counterclockwise unless specified otherwise. Is that even true? No, you just always have to specify. And so what that winds up looking like, let's say I say that my vector is 4 meters above the x-axis. It's got a magnitude of 4 meters, and it's 30 degrees above the x-axis. You actually kind of want to start from the end. We start at the x-axis. We need to go above it, so we rotate above. We do this by 30 degrees. 30 degrees. And then when we draw our arrow, we make its size 4 meters. So if vector A is 4 meters, 30 degrees above the x-axis, that's what that would look like. 20 degrees north of east is another way to do that. When it says north of east, again, you start from the end and work your way backwards. East is where we start. Never eat soggy waffles. East is where we start. We need to rotate by 20 degrees, and we need to go to the north. So 20 degrees north of east would look something like this. Widdershins is the German word for clockwise. I think it's funny that should say anti-clockwise. Or counterclockwise. Whoops. So that's one way to represent vectors. A lot of times, because you have the magnitude of a vector, this is a way that they get represented, but typically that's not the one that's particularly useful for the reasons that we just went into, where it's really hard to add them together, right? So instead, we tend to represent vectors with components. And so to do that, you'll need two axes that are orthogonal. Normally that'll just be x and y. For hills specifically, we do mess with that, and you can if you want to. What it's showing you in the components is how, there's a lot of ways to say this, the projection of the vector along that axis is one of the big official ones or whatever. But honestly, just like if you're looking at it and you're like, well, this goes two directions. It goes left and it goes down. How far does it go left? This far. That's the left component of it, or the x component of it. How far does it go down? This far. That's the y component of it. So taking what I just said and making it so you can actually see it, let's say we have this vector that looks like this. And I'm able to say this thing goes two directions. It goes to the left, and it goes, down. If I draw the x and y axis, one from one end of the vector, the other from the other, and it'll make a rectangle if I do it from the other side. So if I start from this end and I do the x, and I start from this end and I do the y, at the points where they intersect, those will be where your components end. So this one goes to the left, and it goes to the left by this much. Alternately, I could see that it goes to the left here by the same amount. It also goes down by this much, or it goes down by this much. You don't have to draw both of these, but I just sort of did it to show that you could draw either. Let's say this thing goes down by 5 and left by 3. The components of this thing would be -3, -5, because it's going left and down. So if we were to represent this vector, it would look something like this. -3, -5. And this would be our vector in component notation. If we want to find out what it is in angle magnitude notation, that we'll cover next time. So, we've done this. If you don't have a grid, finding the components is terrible because you have to do trig, and it's a whole big thing that we need to learn trig in order to do. Not right now. So, goodbye, YouTube. There will be a link to the PowerPoint as well as a link to some practice sheets with answer keys in the description of the video. I hope you have a fantastic day. And again, sorry this one ran a bit long.